Welcome to this video on Measures of Variation Part 2, Standard Deviation as a Non-Resistant Measure of Spread. Let's get started. After watching this video, you will be able to demonstrate that standard deviation is a non-resistant measure of spread. Standard deviation is a non-resistant measure of spread. The standard deviation is a non-resistant measure of spread. This means it can change drastically in the presence of one or more outliers. To demonstrate this, let's return to the standard deviation example from the previous video. In the previous video, we calculated the standard deviation and we found it was around 14 points. Remember, we had 5 different test grades and we averaged those together, and then we found the average distance from the mean, which is the standard deviation. So this time, let us augment these 5 test scores, or whatever grades they are, and pretend that there was a 6th score that was a 0. So here we go. So let's pretend that there were 6 tests or grades in general, and that one of them was a 0. So before we do anything else to calculate the standard deviation, we're going to have to recalculate the mean, because as soon as we change our data set, we change our average. So as you can see over here, we are recalculating our mean. The sum of all the numbers is the same since we're adding a 0. However, the difference in the mean calculation is that now we're dividing by 6 because we have 1, 2, 3, 4, 5, 6 data points instead of 5. So our new mean or average is 70.5. So now that we found our mean, we can find the average distance from the mean, and we do that by first subtracting the mean from each data point. And as you can see, we've done that here in this table. So now that we have found the distance from each data point to the mean, we need to square all of these values. And so we've done that here. And then once we find the square of those distances, we add them all together to get 6,765.5. So how does this number relate to that equation that we have for standard deviation? Well, believe it or not, what we've done is we've found the distance. We found x minus x bar, the distance from each data point to the mean, and that was these values right here. Then we squared them right here, and then we added them all up. So in other words, the sum of x minus x bar quantity squared is 6,765.5. So I can replace this whole expression here under the radical in the numerator with this number right here. So let's go ahead and do that. So now we have 6,765.5 divided by n minus 1, and again, we're still taking the square root of that whole thing. So now we have to ask ourselves, well, what is n? What does that mean? Well, recall, n is the number of data points, and we have 1, 2, 3, 4, 5, 6 rows of data, 6 data points, so n is going to be 6. So we have 6 minus 1, or 5. So here is our new formula, and this is something we can very simply type into a calculator. I've put it into decimals, and so we crunch those numbers and we get about 36.78. So what does this mean? The new standard deviation, with that addition of the outlier, which was the 0, is about 37 points. And remember, in our first example, when we only had 5 data points and no outliers, our old standard deviation was 14 points. So let's just compare these two numbers, 14 to 37, right? So if I doubled 14, 14 times 2 is 28. We've actually more than doubled the standard deviation, or the average distance from the mean, just by throwing in a single outlier. So we have demonstrated that the standard deviation is very sensitive to the presence of one or more outliers. In other words, it will change drastically if you throw in one or more outliers.